4.6, linear approximation and differentials. All right, if I have some function that's continuous, maybe like a polynomial format, we can graph it. Let's just say we have something that looks like this, kind of curvy. Y equals f of x. So who knows what it may be? It's kind of looks like a logarithmic kind of whatever. Might just be a polynomial. We know if I pick some x value has a coordinating y value. So let's say a comma f of a. Let's say we can find a tangent line at a, right? So that is the derivative, right? So y is equal to f prime of a right here, slope of the tangent line, right? This line right here is the tangent line at a. We're also going to call this L of x, the linear approximation. Okay. So if I want to figure out what is the slope of the tangent line, there's an alternative way to approximate it without having to go through the complicated derivative. If I pick a point, 2 points in effect, that are very, very, very close to A, you got 2 points, right? If you have 2 points, can you always find the equation line? You find the slope between the 2 points and then plug in one of those 2 points into y equals mx plus b. Boom, you got a line, right? That line is not going to be the tangent line, but it's going to be very, very close to that tangent line because we know the tangent line is the slope of the tangent line at A is the derivative, right? Those 2 points, yeah, they're very close to each other for the approximation, but in a sense, the calculus of the tangent line, those points, in a sense, they're not equal to each other, but they are basically equal to each other, right? So they're so close, they're basically touching. All right, so L of x is equal to, now this is just formatting. I don't care if you memorize this format, it's just trying to get you guys to put on your big boy drawers and panties or whatever to look at the calculus format. L of x is f prime at a times x minus a plus f of a. Okay, what is that? You make the remember that from algebra? That's that same thing, right? The f of a is a y value, right? Bring it over to the other side. So subtract it. So that's y minus y1 is equal to m slope. So we'll find the slope of the tangent line times x minus x1. X1 and a, that's the same thing. All right, so like I said, I don't care if you memorize that format, but it just gives you a little technique sometimes. Oh, I need to figure out the slope of the tangent line at a, calculate that real quick. That's easy, we know how to take the derivatives. Find the derivative of the line, plug in a, you got it. And then x minus that a plus f of a, that approximates the entire equation for you. So this is L of x is the linear approximation to f at a. F of x is close to L of x. For x near a. And the thing about using that notation I just put up there is L of x is defined at a from f of a and f prime of a. All right, let's say we are driving at a constant speed. And you record the number of seconds it takes to travel between two consecutive mile markers. All right, we know this. If it takes 60 seconds, in 1 mile, then it's 60 miles in 1 hour, right? That's an easy conversion, right? Keep your foot on 60 miles per hour, it would travel exactly 60 miles in 1 hour. Every 60 seconds, every minute you traveled 1 mile. All right, so now suppose you travel 1 mile in 60 plus X seconds. So you're going a little bit faster, right? So example, 62 seconds, X is 2, right? If you're going faster, X will be a negative. I mean, if you're going slower, X will be a negative number, right? Let me erase that and put that example. Let's say 57 seconds it took. X is -3. So our average speed in miles per hour. They use the notation S of X. Again, you can use the formula distance is equal to rate times time. So this is distance divided by time. So how far would you travel in 1 hour? That's your time right there, 60 plus X over 1 hour, 60 times 60, right? So this can be rewritten to, if you wanted to put it as 3,600 times 60 plus X to the -1 power, if you want to do it that way. All right, so I do have my average speed function, right? So I can graph that if I wanted to, but if I'm saying, okay, what is the speed at this particular time? Okay, I can go ahead and do the derivative, calculate it out, but I can do a quick approximation really fast. So the idea is find a linear approximation to this. So I'm going to need S prime, right, of X. The chain rule can come into play really easily for this. -1 times 3600, -3600. Keep the parentheses. To the 1 less power, -1 minus 1 is -2, times the derivative of the inside is a 1. All right, so if I would say, if it took exactly 60 seconds to travel between here at this mile marker to the next one, X is equal to 0, right? Okay, so exactly 60 seconds between markers, X is equal to 0. So I can say that S of 0, going to the function, 3600 divided by 60, that is 60. S prime at 0, putting 0 in here, that's 60. We could put this, make it a little bit easier. -3600 divided by 60 plus X all squared, right? Putting 0 in here, 60 squared is 3600. So that gives you -1, right? -3600 over 3600, -1. So linear approximation L of X is always going to be equal to this easy little formula. S of 0 plus S prime of 0 times X minus 0. S of 0 is 60. S prime of 0, -1, times X minus 0. That's just 60 minus X. So now you can just use this to approximate all values that are near our A, near our 0. So if I'm 62, X is 2, that's near 0, right? So you could see, just say, go back to this function, just say this graph represented that average rate, that average speed right there. So as long as I'm close, this line is still very close to the tangent line, right? But once I get over here and I pick this point and this point, this is not the tangent line anymore, right? So the further away I get off of the function away from that A, the line is starting to tilt, right? But when you're really close, that line tilts a little bit, but very, very little. So still choose values close to A, and you can figure out what the speed is quickly. Okay. Speed at X equals 0, 60 miles per hour. At X equals, let's see, we'll put in here 2, 58 miles per hour. At X equals if you want -3, that's 63 miles per hour. Because you're getting to the next mile marker a lot quicker. Right? So keep it near 0, right? So again, if you start going, all right, what if I made X to be 10? It's not going to approximate it that well. Okay, you're being in the ballpark, but there's just a quick way to figure out the slope of the tangent line. It's real. All right, so that's more of a real world application, I would guess. You probably say, let me just look at the speedometer. Right? But what if you're in the back of the bus or something? Like, I wonder how fast this bus is really going, right? Well, you can kind of click your stopwatch, right? And when you get to the next mile marker, see how long it took. And if it took less than 57 seconds, 60 seconds, you went faster than 60 miles an hour, right? If it took more than 60 seconds, you're going more than 60 miles an hour. How fast? Then you can go through this process if you want it, since you'll be bored on the bus doing nothing, right? Get some calculus, why not? All right, here's another example that's really useful mathematically without calculators in a sense. All right, find the linear approximation. To the function f of x, which is equal to the square root of x. At x is equal to approximate, x is equal to 1 to approximate the square root of 1.1. All right, so we have our function. That's the nice curvy line, right? We can draw it if we wished. That's that. Square root of x. And I want to say at 1, we know the square root of 1 is 1, right? 1.1 is what? Well, 1.1 is very close to 1, right? So it's going to be very close to the square root of 1, not exactly 1. It's going to be 1 point something, right? We want to know what that something is. You say, well, I've got to calculate for that now, right? But the linear approximation could do this. So if I say, okay, well, we have to find f of a and f prime at a. Okay, so x is 1 right there. So I would say f prime of x is equal to, you have to know what the derivative of the square root of x is, 1 over 2 square root of x, right? So now I plug in 1 into both. F of 1 is the square root of 1, which is 1. F prime at 1 is 1 half. The linear approximation is f prime at 1 times x minus 1 plus f evaluated at 1. I got these two numbers. This is 1 half. Of x minus 1 plus f of 1 is 1. So I use this to approximate. The square root of 1.1. How far is 1.1 from 1. That's our x. Use x is equal to 0.1, right? .1 minus 1 is negative 0.9. It's negative 9 halves. Plus, this is not negative. What's wrong here? X minus 1. Where did I mess up? 1/2 x minus 1 plus 1 . Oh, L of 1.1. That's what we're doing. The difference between them is 0.1. So L of 1.1, that's what we're doing. 1.1 goes in there. Sorry. All right, so we're approximating 1.1. So we're going to evaluate 1.1 in there. 1.1 minus 1 is 0.1. Half of 0.1, 0.05. That's 1.05, approximately, right? So the square root of 1.1 is approximately 1.05. And we can verify what is the real value. .0488. So pretty close. If I'd say approximate 1.01, you can do the same process, just plug in 1.01 into your approximation formula, right? So we got the numbers getting closer and closer to the actual square root of 1, so that's going to give us even more accurate number.
So you do this and do like subtractions and when you're given the same, like when you're given a point, it's like the same thing with different like stuff. Like again, let's say you were given like a point like I don't know, x equals like 4, and like the number of approximation would be like 4.9 or something, or like you would just subtract them.
Yeah, you're going to take a nice number that you know of, like the square root of x. We looked at the square root of 1. So I'm going to choose numbers that are very close to there.
Yeah.
So if I'm looking at like, say, approximate 9.2, the square root of 9.2, let me look at the square root of 9 in there. And then square root of 9.2 would be evaluated into our linear approximation function. And we can do that either mentally, maybe need a calculator, but if you're already using a calculator.
Yeah.
Yeah. You can see in the next examples too that you're gonna, most of these are like approximate a cube root, approximate a square root, those kinds of things. But you want to pick the nice, perfect squares and perfect cube roots. That's gonna work. All right, so if I say, let's look at this, approximate the square root of 0.9. You're only off by 1/10, right? So that's pretty close to the square root of 1. So I could use this approximation too. So I put L of 0.9 in that formula. That was still 1/2, what's it, times 0.9. minus 1 plus 1. That's negative 0.1 over 2 plus 1. That's negative 0.05 plus 1, so that's 0.95. Now I'm doing all this mentally, so you can double check it. Sometimes with all these decimals and things, you do want to verify with the calculator. You will have a calculator. So 0.1 divided by 2, that was the 0.05 negative. Okay, so 1 minus that is that 0.95. And then you can do the square root of the actual 0.9 to see how close you are to that. That's pretty close, 0.9486. Now, if I say approximate the square root of 2.8, we're going to be off. Something like that. So we got 1/2 times 1.8 plus 1. Half of 1.8 is 0.9 plus 1. That's 1.9. Is that close to 2.8? Probably. I mean, it's probably okay, but it's not as accurate as the others, right? So we got square root of 2.8. 1.67. Okay, it's still recording. Good. So if you go back and watch this, it might be a little bit of a delay between where we left off and now. All right, so we said that the square root of 2.8 is actually 1.67, right? So that's far off, right? The linear approximation is only good when your x and your a are very near each other, right? So the difference between x and a is basically extremely small. So L of x, which is f prime of a times x minus a plus f of a. So it's not really hard to remember this little formula, right? It is that point slope form of the line, which is really all it is. But just knowing in terms of f prime of a and f of a, right, is a good approximation to the function f of x. If x minus a is sufficiently small. Now let's do a trig function. Let's do find linear approximation of x to sine x at x equals 0, or our f of x is equal to the sine of x, 6. So x is 0 degrees, 0 radians. Right now it didn't specify, but we can assume just radians now. So if I choose angles that are very close to 0, I can use this approximation and calculate their trig function value instead of having to do opposite over hypotenuse and all that stuff and using calculator and draw the right triangle trigonometry. This is just really a quick way to evaluate. So I would first say, okay, f prime at x is derivative of sine, cosine. All right. So now I plug in 0. F of 0, sine of 0 is 0. F prime at 0, cosine of 0 is 1. All right, so my linear approximation is in that format just had up here. F prime at 0. Let's just rewrite it all up. F prime at 0 times x minus 0 plus f of 0. F prime at 0 is 1. X minus 0 plus f of 0, 0. It's just equal to x. So it's just approximated by x. So if I say What is the sine of 2.5 degrees? Linear degrees, so we're going to use everything in radians, right? So I need to do a calculation in radians. So this is approximately equal to, well, let's do 2.5 degrees. Change over to radians. Remember pi times 180? This is, you could do the arithmetic by hand if you wish, but this is pi over 72, which is 0.04363. So if the sine of 2.5 is approximated by just x, it's going to be this right here, 0.04363. Let's see what that is in the calculator. Sine of 2.5 degrees, put my calculator in degree mode. Already in degree mode. 0.4361. Not off that much. So as long as I am close to the zero, my approximation is pretty close. And think of the graph too. Graph is nice and smooth, right? So the slope pretty much is the same until you start getting closer and closer to that peak at the top, right? Where it starts to change direction. The slope changes a lot after you've extended your x's a lot. But if you're keeping your x's closer to the zero, that slope of that tangent line is pretty close. All right, a variation on linear approximation. We know our function f of x is approximated by the linear approximation function, which we just saw again, f prime at a times x minus a plus f of a. If I start rearranging this, I have these two equations, but these two are interchangeable pretty much, right? So I have like f of x is equal to f prime of a times x minus a plus f of a. Let's manipulate this equation just a tad, just the same way we did earlier where I showed you that this can be put in point slope form. If I bring f of a, f of x minus f of a, is equal to f prime of a times x minus a, right? Notice on the left side, f of x, it's an output, right? It's an output, it's a y value. F of a is another y value, right? So supposedly these two y values are very close to each other. These ordered pairs are really close. This is a change in y, right? F prime of a is still our slope of our tangent line. X minus a, those are the inputs, right? X is x. A is an x value. That's just along the horizontal x-axis, right? Just two different ones. So the difference between those two is a change in x. So nothing new. This is really just fancy college algebra, all we're doing. If I divide everything by changing x, f prime of a is equal to change in y over change in x. Change in y over change in x. That's the slope, right? That's nothing new. So if I'm looking at if I didn't divide by this, I can just say change in y is equal to f prime of a times change in x. There's so many ways to manipulate this. Now I can say, what is change in x? Change in x is your x minus a, right? So change in x was x minus a. Y'all know the triangle notation delta before, right? Y'all seen that before? Delta means change in y or x, right? All right, note that a and x equals a plus change in x. I'll go back and show you that. X is equal to delta x plus a, or a plus delta x, right? Either way. These are in an interval on which f is differentiable. So I mean, all these x values that are along your x-axis, okay, correspond to some part on the function. The function is differentiable, right? So we can take derivative of that. Okay. So if I ask you, change in y, which is equal to f of x, which is x to the ninth minus 2x plus 1. When x changes, from 1 to 1.05. Now you can go old school and figure this out. Evaluate x as 1, evaluate x to be 1.05, get the two y values, subtract the two y values, that's your change in y, right? But we know change in y is equal to, right here, f prime of a times change in x. So if I look at f prime of 1, so we got, yeah, you need to go back and see. This was x minus a, okay? So we're looking from 1 to 1.05. So where I'm starting from, f prime at 1, plug that in. Let's see what f prime is. We didn't do that. That's 9x to the 8th minus 2 times it, just 2. Putting in 1 in there, that's 9 minus 2, that gives 7. We'll put 7 times the change in x, 1.05, minus 1. That's 7 times 0.05. The change in y is going to be 0.35. The actual change in y, I would have to do f of 1, 1 to the ninth minus 2 times 1 plus 1. 1 minus 2 is negative 1 plus 1 is 0. That's not right. or is it, wait, 1 minus 2 is -1. Yes, right, +1. And then I'll do f of 1.05. Now this is where I have to bring out the calculator. 1.05 to the 9th. Minus 2 times 1.09. Plus 1. That's that number, 0.37132, 133.37133. So the difference between these two, you can see is 0.37133 minus 0 is 0.37133. That's still approximated. That's pretty close though. 0.35, 0.37, you're off by 2/100ths, right? So again, as long as the change in x is very small, the change in y can be approximated fairly decently, right? So the change in x is 0.05, right? That's very small right there. Yes.
Where'd you get the 0.09?
The 0.09. 2 times 1.05. That's supposed to be a 0.05. Thank you. Typed it in wrong. That's still wrong. Oh, that's 1.05 to the 9th power minus 2 times 1.05 plus 1 is 0.45. All right, so this is not right then. Should say kept it at 1.09 or closer. 0.45. 0.45. It's still 1/10 off. It's close, not extremely far off, but it's still an approximation to what the change in y would be. So just as a recap, for all x near a, f of x is approximately the linear approximation function, which is f prime of a times x minus a plus f of a. And the change in y is just rewriting this equation, right? We just saw just manipulating it around in terms of changes. It's just approximately f prime at a times the change in x. This leads up to what's called differentials. All right, so y is f of x is differentiable. On an interval containing a. The change in y is equal to f of a and that change in x. So you start off with a, let's just say a is 5. The change in x, how do I get to the next number? I don't know, add some little small significant little part to it, okay? Minus f of a. This is the difference of y values right here, change in y, right? So this is the further x value, a plus change in x. right? You evaluate it, get your y value. Your left x value, your a, evaluate it. So we'll just draw a picture of that in case you need to. Here is a, and then we've got a change in x. So right here is a plus a change in x. This right here is f of a. Maybe over here is f of a plus change in x. The differences between these two is your change in y. This is the exact change, right? This isn't approximating it, what we just did using the derivative evaluated, right? The approximate was change in y is equal to f prime at a times change in x. All right, a change in x. We're going to call it something else now instead of using triangles because triangles take too long to draw. You got to put in some calculus notation. So two new variables called differentiables. Dx, we saw that already. This is a change in x. Dy, it's a change in y. It's changing the function, right? Changing f, which is approximated by the change in L. Right? So a change in y, making this note substitution, dy is equal to that change in L, which was the derivative evaluated today, times the change in x, which we know that this is f prime at a times dx. So it's just, all this is just making substitutions in notation. That's all it is. So therefore, this equals this. So dy is equal to f prime at a times dx. You saw dy over dx before? Dy over dx is the slope of the tangent line, right? It's just a different notation. Which is f prime at a. That notation. It's Leibniz notation. That's all it is. So if I ask you if, easy example, if f of x is equal to, let's say 4x squared plus 5x plus 2, what is dy? You can easily just do this. Dy, the change in y will be equal to right here. F prime is 8x plus 5 times the change in x dx. That's it. I didn't give you any specific values to plug in, so I don't know. That just gives me the change in y. That's an equation or formula that gives me the change in y. So all you do is take derivative and tack on dx at the end. So if I ask you this kind of notation, that's it. Dy is equal to derivative times dx. That's it. Very simple. You can do a trig function. If I say if f of x is equal to 3 times the cosine squared of x, dy is equal to what? Dy, all right, so this is 3 times cosine x all squared, if you want to look at it that way, right? Just the cosine is squared. So chain rule can apply. So f prime, 2 times the 3 makes 6, times the derivative of the cosine of the x. Actually, I probably ought to be doing, sorry. So 6 times the cosine of the x to the 1 less power. I could have did the product rule. That's what just went in my head just a minute ago. To the 1 less power, then times the derivative of the inside function cosine of x primed. And then this is all times dx. What's the derivative of cosine? Negative sine dx. Clean it up a little bit. Let's put the negative 1 out in the front. So negative 6 cosine x sine x dx. Anybody see another format you could put in? I'm just looking at my notes. You don't have to go any further than that. That's perfectly fine. But just to throw in some trig, 2 times sine x times cosine x is the sine of 2x, right? So if you want to make that where it's only one trig function involved, you could say this is negative 3 times 2 sine of 2x. And that's 2 sine 2x, sine of 2x, right? Dx. This is really leading into a lot of stuff that you can start seeing in Calc 2. Because where I'm going with this, remember I told you last class period that you've learned just about almost everything you needed to. Now we're going to start going in reverse. I'm going to start going in reverse by using what we call antiderivatives, integrals, those kinds of things. And in those antiderivatives and integrals, you see all this dx notation. Like, what is all that? That's where this is coming from. Okay, so you'll make some substitutions eventually. And especially when you get to Calc 2, a lot of this right here, you'll look at this and you're like, okay, what's the antiderivative of this? How do I get back to 3 cosine squared? Got to recognize a lot of these things, okay? And then go backwards. It doesn't look too easy, right? So. All right, any questions?